al ciclo de conferencias Universidades por la Ciencia, organizado por Fundación UNAM, el Colegio Nacional y el conjunto de universidades y centros de investigación del Consorcio Universidades por la Ciencia. En este ciclo tenemos conferencias sobre diferentes temas de la investigación científica y el día de hoy tenemos una muy especial por el profesor Uisdean Nicholson de la Universidad Heriot-Watt en Edimburgo. La conferencia es sobre el cráter NADIR que está en las costas de Guinea en la parte de África y que tiene una edad cercana al cráter de Chicxulub. El profesor Nicholson tiene un muy amplio rango de temas de investigación que incluyen evolución de cuencas, procesos sedimentarios, la parte de clima y la parte de desastres o riesgos asociados a fenómenos geológicos. Su investigación se caracteriza por ser multidisciplinaria y este trabajo que hace sobre el cráter NADIR, yo creo que es un muy buen ejemplo de lo que esto representa. Welcome to the Universities for Science Seminar Series organized by UNAM Foundation, the Colegio Nacional, and the group of universities and research centers of the Consortium Universities for Science, with universities and research centers in Mexico, US, UK, Spain, Brazil, Argentina, Chile. Today, we have a very special conference by Dr. Uisdean Nicholson. He is a professor of geosciences at Heriot-Watt University in Edinburgh. Dr. Nicholson has a very wide research interest, including basin evolution, sedimentary processes, ocean gateways, the thermaline circulation, climate, and geohazards. And his studies are characterized by a multidisciplinary approach, and the study of the NADIR crater offshore West Africa, I think is a very good example of his studies. Professor Nicholson research contributes also to the development goals of the United Nations, these 17 goals on climate and marine life. And this seminar series is part of the International Year for basic sciences in sustainable development. So we are very pleased to have Professor Nicholson accepting this invitation to give this seminar. And well, personally, and for our research group, our students, we are really very interested in the findings of Dr. Nicholson on the NADIR crater, because well, the age of the impact is at or close to the Cretaceous Paleogene boundary, and well, we have been studying the Chicxulub crater for quite a long time, and this is a very interesting addition. So we are particularly interested in keeping and expanding a collaboration with Professor Nicholson. So thanks very much. And we welcome questions, comments in English and Spanish. Thanks very much, Professor Nicholson. And now we will ask our president of the UNAM Foundation, Dionisio Meade, to give a welcome remarks. Muy bienvenidos todos. Preguntas en inglés y en español son bienvenidas. Y le pasamos la palabra a nuestro presidente de Fundación UNAM, el licenciado Dionisio Meade. Nos acompañan también en el presidium la directora ejecutiva de Fundación UNAM, licenciada Araxi Rodríguez, la presidenta del Consorcio de Universidades por la Ciencia, Araxi, Urrutia. In the panel, we are joined by the Executive Director of UNAM Foundation, Araceli Rodriguez, and the President of the Consortium of Universities for Science, Araxi, Urrutia. Thanks very much.
Pues muchas gracias a todos y bienvenidos nuevamente a esta presentación de nuestra serie de Consorcio de Universidades por la Ciencia. Thank you very much, Professor Nicholson. You are very welcome to be with us here, and we are very happy to hear your presentation. Esta presentación pues prácticamente culmina con la serie de pláticas que hemos venido a lo largo de este año, y que en esta última serie, a partir de agosto a la fecha, pues cumple ya 14 transmisiones, y como son investigaciones en curso, pues se han tocado temas muy diversos, como el cambio climático y la salud, la autocepción, las explosiones en nuestra galaxia, la construcción de moléculas para la exploración del espacio químico, la evolución de las especies, y en particular, en este caso, sobre el tema de la lagartija. Y yo creo que esto ilustra el vasto campo de investigación científica que está abierto para todos los jóvenes que hoy nos están escuchando. Realmente para nosotros ese es el principal objetivo, el fundamental, de poder contar con estas pláticas, que se les abran a los jóvenes que están haciendo sus estudios o que están optando por su vocación profesional, todas las capacidades y todas las aptitudes que ofrece la ciencia, en campos tan diversos como los que el propio profesor Nicholson habrá de describirnos en su plática de hoy. Agradecemos mucho al Colegio Nacional por haberse sumado a Fundación UNAM en este esfuerzo, a la universidad, a todos quienes con sus redes nos permiten participar en este esfuerzo, que se ha vuelto ya pues un esfuerzo que no reconoce fronteras, porque se puede escuchar tanto en el país como en los países de origen de los conferencistas que nos acompañan, y eso le da una gran diversidad y una gran capacidad de difusión al conocimiento científico. Nos motiva mucho que ustedes, los jóvenes, nos escuchen, y seguramente motivará más al profesor Nicholson las preguntas que ustedes hagan y el interés que manifiesten en tratar de conocer un poco más de la ciencia. Nosotros hemos dedicado pláticas a Chicxulub, y tener la oportunidad de hablar ahora de este espacio con una antigüedad similar a la de Chicxulub con el NADIR, va a ser para nosotros bien interesante, y nos va a ilustrar también si tenemos capacidad de conocimiento, si hemos explorado suficiente el Chicxulub, qué de los descubrimientos de esta serie del NADIR son similares, y cómo podemos intercalar cómo podemos intercambiar estos espacios de información que una y otra investigación nos ofrece. Muchas gracias a todos, les agradecemos su presencia, agradecemos de manera particular al Colegio Nacional, al profesor Jaime Urrutia, a Araxi, que ha sido pues artífice en la gestación de estos eventos, y agradecemos a todos que nos acompañan en esta presentación, que habremos de escuchar con el mayor interés. Muchas gracias.
Thanks very much. Gracias. And Professor Nicholson, thanks again.
Great. Thank you very much. It's over to me, I suppose. Yeah.
Yes. Yeah, please.
Okay. Well, thank you very much, first of all, for inviting me, Jaime and Dionisio. Thank you for the kind words. And yeah, it's a pleasure to be here and be able to present to the audience, who I can't see, but I can see you two today. So what I'm going to present to you today is not quite what is on the title here. This is one of the headlines that was published in one of the British, in fact, one of the international newspapers shortly after this paper was published. Not one, but two asteroids might have slain the dinosaurs. We're going to go with a much more nuanced title today, which is the one I gave to you, Jaime, and the one that was advertised in the poster, the NADIR crater, a new candidate KPG impact structure. So at the moment, this is just a candidate structure, but it's very exciting candidate structure, and particularly the association with the KPG, the timing of the potential impact. The co-authors in this are Veronica Bray from the University of Arizona, Sean Gulick from UT Austin, and my PhD student, Benedict Adomahor, here at Heriot-Watt. Just also some acknowledgements here for data. So the funding, some of the funding for this comes from UKRI, NERC, and we also have data provided by TGS and Western GECO or Schlumberger for this. All right, so this is the structure of the seminar today. So I'm going to talk to you first just a little bit. I actually don't really know the detail of the audience, so I'm going to give a little bit of an introduction to impact cratering, quite high level. Then I'm going to talk about, or I'm going to describe the NADIR crater. What are the observations that we made that make us think that this might be an impact, hypervelocity impact crater? And then we're going to spend some time looking at the environmental consequences of the crater or of the impact event. And then finally, I'll get onto the relationship with Chicxulub at the end, and also I'll describe what we're going to do next here, because we do have a drilling proposal that's been submitted to go and drill this crater. All right, so first of all, I'm just going to start with some basics and describe the introduction to kind of different types of impact craters on Earth. So this is a very simple classification system this came from, I think, I can't remember the exact paper that I got this from. No, and the citation should be on here, so my apologies for that. But this is one of the classic cross sections across a simple crater at the top and a complex crater at the bottom. And the simple crater on the right-hand side is shown here. Let me just put in my highlighter. Okay, so here we have a simple crater with a raised rim, a bowl-shaped cavity, and cross section. You can see it's just a very simple concave up bowl shape. This is what you would get if you throw a pebble in a crate of sand or onto a beach. Anything from that size, anything up to about 3 kilometers diameter would have this kind of complex morphology. Anything larger than that size on Earth, at least, would have a different morphology, because the associated energy here is much higher. We get what's called a complex crater with a central uplift, where the rocks or the sediments below the crater floor rebound and move more or less like a ductile fluid temporarily vertically upwards into the crater that's been evacuated, the former transient crater. You can see the morphology is a little bit different. The rims are similar in both scenarios, but the morphology here is a little bit different, and you might expect a little bit more impact melt in association with these complex craters. So again, this boundary is important. Anything larger than 3 kilometers on Earth, you would expect to have a complex morphology. I'd just take a little bit of a step backwards and think about where we've seen impacts in historical timescales. Well, we haven't had any large impact on Earth in historical timescales. The closest thing that we've had was the Tunguska event in 1908, which was caused by, most likely, by a approximately 50-meter asteroid that exploded in the air several kilometers above the East Siberian surface and destroyed an area of some 2,000 square kilometers. You can see from these circles that I've drawn here the approximate visible radius of the fireball and the audible radius of the explosion. This is from recorded incidents of people hearing it, documenting that they've heard it or seen the fireball. So that's about a 12 megaton explosion in association with an asteroid that size. 2013, there was a 20-meter asteroid that entered the atmosphere, and again with an air blast above the Earth's surface in Siberia, West Siberia, this time in Chelyabinsk. This is a 0.5 megaton explosion, but neither of these is quite large enough to reach the Earth's surface. So nothing larger than 50 meters in historic records. If we go further back in time, we can see here an image from the Earth Impact Database, or the Impact Earth Database, I should say, that's very recently published. You can access this online or through Osinski et al. 2022's paper. There are 200 confirmed craters on Earth. So in this case, these impactors have been large enough to reach the Earth's surface. These are confirmed in that there's some diagnostic criteria for impacts, so shocked quartz, shocked mineral phases of different kinds. Obviously clustered in North America and Europe and Australia, also a few in North Africa. Chicxulub sits here, as you well know, in Mexico. But only of these 200 craters, only 20 of them are confirmed marine target craters. So that's asteroids that impacted first the sea before also forming a crater at the seabed. There are 42 additional impact deposits also shown here in blue. So the closest one to me is here in northern Scotland, the Stackfather member, which is a Proterozoic impact event. What does that crater distribution look like through time? Well, much as you would expect. You can see that we've got age on the y-axis here, the number of craters on the x-axis. So we have a relatively high number of craters in recent geological time, but that tails off significantly as we get into the Proterozoic in particular. And it follows the kind of trend that you would expect, except for this area in here, just shown in more detail here in the Ordovician. This is what's the only confirmed impact cluster in the geological record. So this is a period in geological time when the impact cratering rate was significantly higher than you would expect from kind of background asteroid near Earth objects colliding with the Earth. So that's around 466 million years ago. And within that same period of time, within that impact cluster, we also have the only documented, as I understand the present day science, at least, to be the only confirmed impact doublet. So that's two craters that are formed close together, that are formed by probably a binary asteroid that collides with Earth. So one large asteroid with one small satellite. So one case of an impact cluster, one case of a binary impact doublet in the whole cratering record. I want to talk about impact frequency because this is important later on when we're thinking about what the relationship might be between NADIR and other events. So we get a 50-meter asteroid colliding with the Earth's surface. So this is a Tunguska size event, around about once every 9,000 years. This is from the Blanda Artemida database in 2006. So they've got various trend lines on here. I'm using the red line here as the best, what's likely to be the best gradient, the best trend. We have a 150-meter asteroid colliding with the Earth's surface every 100,000 years. So this is what we would expect to be large enough to form a complex crater. So this 150-meter asteroid would form a crater typically of about 3 kilometers. We have a collision rate of about once every million years for a 1 kilometer asteroid. This is often a rule of thumb threshold for something that has a real planetary impact, depending on the impact stratigraphy, the target stratigraphy. And something really large, Chicxulub or that kind of scale, so larger than 10 kilometers, which is likely to form to cause mass extinctions once every 100 million years or so. All these assumptions are, I should say, are for chondrites, so stony meteorites, stony asteroids, sorry. So given that, how many craters are missing? What kind of preservation do we have? These are back of the envelope numbers that I put together for this, but what we would expect to get is a complex crater, as I just mentioned, once every 100,000 years. So there should be about 10,000 of these complex craters since 1 billion years ago. In that impact crater database, we only have 138 of these craters. So I think we have approximately 1.4% of craters discovered, preserved and discovered. But only 20 marine target craters, that's only 0.2% of craters, marine target craters, are discovered. So a really tiny proportion of those craters that hit the large part of the Earth's surface, 70% of the Earth's surface, only a very small proportion are preserved. So there's a lot that we don't know about these in terms of what their consequences might be. Okay, that's the first part, just to frame the discussion. So I'm now going to talk about the observations from West Africa that led to the discovery of this potential crater. So this is where we are in terms of our geographic location. This is West Africa. Here we've got Guinea, and we've got Guinea-Bissau to the north. So this is Africa as it was back in the late Maastrichtian or early Paleogene. And the Guinea Plateau is located here, just offshore Guinea and Guinea-Bissau, present day. The plateau is about 400 kilometers in width, so that's the width away from the coastline towards to the continent ocean boundary at the edge of the plateau here. And it's got this terrace. It's relatively shallow water in the inboard part, but this terrace, which goes down to about 1,000 meters water depth in the southwestern part. And a few years ago, I was provided with this seismic database that you see here, this 2D seismic reflection database, in order to develop a drilling proposal, actually, on a very different topic, looking at paleoclimate, paleocirculation, associated with the opening of the Equatorial Atlantic Gateway. So that's the separation of South America and Africa. You can see what the seismic looks like here. So we have the shallow Guinea Plateau here. We have the intermediate depth Guinea Terrace here, and then it gets off into deep water. A couple of things to point out here. There are some Paleogene volcanics in the area. This is the Nadir seamount, from which the crater gets its name. This is a very large seamount that formed about 55 million years ago or so, maybe a little bit younger. On the other side in the north of the plateau, we have Triassic to Jurassic salt, including also some little shallow craters above some of these salt diapirs as they dissolve. So a couple of other things to keep in mind when looking at the geology here. But in general, this plateau records about 150 million years of continuous marine deposition at relatively shallow water depths, from about a few hundred meters down to about 1 kilometer water depth. If we take another line here now, going from east to west, this line transects one of the exploration wells that we have in the region. So we have some dates from this exploration well to constrain the stratigraphy. You can see what the plateau looks like in this orientation. And particularly, I want to draw your attention to this box in here, where we have relatively flat-lying stratigraphy, and then this concave up feature at the top and this convex up feature at the bottom. This feature, the top of this feature, forms at the KPG boundary, so far as we can tell from the seismic reflection data. So within the uncertainty of the relatively low frequency of the seismic. So in the next slide, I'm just gonna zoom in on this box here and show you what that looks like in the depth domain. Just also for reference, at the top of the Maastrichtian, the shelf edge is located here at the red star. So we're off the edge of the shelf here in sort of intermediate water depths. All right, so this is the feature that I just pointed out, but now you're looking at this in the depth domain. So this is seismic reflection data in depth. It's pre-stack depth migrated data, so relatively good depth, good imaging of the crater, but it is two-dimensional data, so it's a single 2D seismic profile. So this is the feature that I first looked at and thought, and scratched my head about for some time, trying to figure out what it was, and the only possibility that I could think of was an impact crater. Why do I say that? Well, this is just the top Cretaceous reflection. So we have this crater floor here at this green reflection, which defines a crater of about 8.5 kilometers in diameter. If I reconstruct what the stratigraphy was like before it was deformed, so these are just flattened regional surfaces, that crater is about 200 meters deep below its regional. And then we have this feature below the crater floor, where you can see that the top Turonian surface here and the top Albion surface or reflection are deformed and uplifted directly below the crater floor. So we've got about a 350-meter central uplift, probably just slightly more than that actually, based on some more recent data. And either side of that central uplift, there's this rim syncline, or there's a synclinal area where it falls below that regional surface. Above that, and so below the crater rim and the central uplift, is this area of intense folding and faulting. I haven't drawn on here the individual faults, but it will show some of them on the next line. And outside of the crater rim, there's this high amplitude facies here. So anomalously high amplitudes reflections, suggesting that the acoustic impedance of the sediments sitting above the seabed at that contemporaneous seabed, the physical properties are very different to those above and below. So something has happened to change the physical properties of these sediments. Within the crater as well, we have a couple of different distinctive facies. We have this facies here between the green and this first red reflection, which are quite incoherent. You can't really map out any individual reflections within that. And then the package above that, where we can see well stratified sediments or reflections that are equivalent to sediments that are approximately the same age as these high amplitude facies outside of the crater. So this looks very much like a complex crater, and that was my first impression. But how to be sure of that with only one seismic reflection profile? So at that point in time, I managed to get in touch with another company. So this is just the same 2D seismic profile with a little bit of annotation on it to show some of the features in here. I should point out as well, actually, that these bright high amplitude reflections at the bottom here that are entrained within the central uplift, we think is a really thick sequence of black shale deposits. So up to 20% total organic carbon within these black shales on the conjugate margin. Okay, so these are some of the parameters I just described here, but that was all in one seismic profile. So at this point, I managed to get hold of another seismic reflection profile here, which is figure 2D here. And you can see more or less the same features. Again, I've just color coded this one according to the stratigraphy. So the Cretaceous here is green, Paleogene is orange, and the Neogene is yellow. So you can see again here we've got this very clear crater floor that's about 9 kilometers, 8.5, 9 kilometers in diameter. We can see the same kind of damage zone outside of the central part of the crater. I'm not sure if I mentioned that before actually, but you can see up here an area where we have extensional faults and fractures potentially forming about 2 crater diameters away from the crater itself. And we see that same thing in this seismic profile here. So that allows us, based on these 2 lines and then some other adjacent lines where we can't see the crater, but we can see the damage zone, allows us to build an approximate shape for the crater. So it's an approximately circular feature that's about 8.5 kilometers in diameter, surrounded by a larger damage zone that's about, from memory, about 20 kilometers in diameter, 25 kilometers in diameter perhaps. So at this point, we have 2 seismic reflection profiles. Do these observations, are they consistent with what we would expect to see for impact craters? So if I plot the Nadir crater on this recent cross plot here from Mazinski et al. Of crater diameter versus stratigraphic uplift, so uplift on the y-axis here, Nadir's got about 400 meters uplift. That number actually slightly updated based on some 3D seismic observations. I'll come back to that later. But the diameter is about 8.5 kilometers. So that fits right on this best fit trend line from Mazinski et al., incorporating all of this data. So very consistent with previous estimates, but also the things like the ratios of the rim height to the crater depth, the width to the depth ratio, the rim to damage zone diameter are all consistent with impact craters that we see elsewhere. So that's very promising, and it really looks like a very good candidate crater at this stage. But the question has to be asked, it's consistent with what we would expect for a mid-sized complex impact crater, but could it be something else? What are the other alternatives? So there are a couple of alternatives that I alluded to earlier. One of these is salt withdrawal. Could we have a salt diapir that reaches the seabed and then partly dissolves and evacuates and collapses? So we do see some salt dissolution features that are relatively common up here in the north of the plateau. They're about 15 kilometers in diameter, or 10 to 15 kilometers in diameter. But these really have a very distinctive and different morphology. We don't see in the case of Nadir, we don't see a diapir extending down to a parent salt body. In fact, we don't see any evidence for parent salt at all in the southern part of the plateau. We don't, with these salt withdrawal features, we don't see any evidence for a crater rim or ejecta-like features. And it's a good 300 kilometers between the Nadir crater and this salt basin. So we think that's pretty unlikely. I mentioned that there were some volcanics in the region. So there are some large seamounts just to the south of here of approximately the same age. So could it be something like a maar? So this is a phreatomagmatic eruption where magma is intruded into water-rich sediments, and that caused this explosive eruption and collapse feature. Well, again, some features might be consistent. You might get something like a raised rim and something that looks like ejecta as it's erupted from the crater floor, and you get this V-shaped crater below that. But with a maar, it really lacks any kind of distinctive central uplift. You don't get a central uplift sitting directly below this, with the stratigraphy deformed into this convex up shape. Also, we don't see any evidence of any igneous intrusions around the Nadir crater. So we think again that this is unlikely, and particularly for Mars, although there are other kind of volcanic features it could be, but Mars on Earth are never larger than 2 to 3 kilometers in diameter. Gas escape. When I first submitted this to IODP, this was one of the responses that came back. Could it just simply be a gas escape structure? These again can form very large diameter pockmarks or craters at the seabed. The example on the top left is from New Zealand. The example on the right is from a paper we published a few years ago in the Falkland Plateau. And again, these form large crater-like features, but again, the lack of a central uplift is really key here. We don't have any central uplifts in these gas escape features or current reworked features. And also these tend to form in clusters. The crater on the plateau is really a standalone feature. It has no, there are no associated craters with it. So in order to really test this, again, I'm just going to try and make sure that this animation works. I got in touch at this point with my co-authors, and they helped also to interpret the data. But the simulations here were run by Veronica Bray at the University of Arizona. So this is an ISAIL hydrocode simulation that we use to simulate a marine impact event using a 400-meter rocky asteroid impacting at 20 kilometers per second and at 90 degrees, so a vertical impact. And you can see here that we managed to generate pretty well something that looks very similar morphologically to the Nadir crater. The diameter is approximately the same. In this case, the rims aren't really very well preserved at this water depth. They are in some other iterations. That's probably to do with the physical properties of the sediment that we allocated. So this is not by any means a perfect model. And the other thing that we notice here is that the resurge. So after initially you form this large rim wave tsunami that propagates away, and when the water comes back into the crater, it carries with it a lot of the ejecta that's deposited outside the crater, which we think is consistent with what we see in the seismic data. So I think that's running again, but I'm going to, in the interest of time, I'll just carry on to just show you some of the different simulations for different water depths. We ran this at water depths going from 200 meters to about 1500 meters. The 800-meter simulation we feel was the best, was the most consistent with the the seismic observations in terms of the height of the central uplift, the amount of deformation in the rim syncline, and preservation of some material on the rims. But it's also the most consistent with the cliniform heights observed from seismic. So we think that this is somewhere between 500, 800 meters, but most likely around 800 meters was the most likely water depth at the time of impact. Okay, so what would the consequences of such an event have been? I've talked about a little bit now about the size of the event, so I'm going to talk through the consequences, and just wanted to bear in mind as I go through this that the asteroid that we think caused the crater was approximately the same size as the Bennu asteroid, which is in near Earth orbit. So this is an image of Bennu from NASA. This is a rubble pile asteroid of about 400 meters in diameter. On the Palermo scale, the particular rating it has of 1.42 on the Palermo scale makes this the joint most hazardous object in near Earth orbit, with a 1 in 1,700 odd chance of collision in the next couple of centuries. So this is just another reference point, recent reference point. This is about 2 times larger than Didymus, which is the smaller of the two asteroids in the binary system that NASA just targeted with their DART mission. If you remember from about a month ago, NASA flew a probe into an asteroid of about half this diameter to see whether they could redirect it. All right, the consequences. The image here shows the fireball from the 1956 atomic test or nuclear blast, 2 megaton explosion. So this gives an idea what this would look like for a relatively small nuclear explosion. The NADIR impactor would have had about 250 times the amount of energy, so 5,000 megatons approximately, relative to this 2 megaton explosion. So, you know, if you're standing at a distance of about 50 kilometers away, so that's me here in Edinburgh, almost looking over somewhere around the distance of Glasgow away, that would still be about 24 times brighter than the sun on your horizon. This would cause 30-degree burns, trees and plants to ignite at that kind of distance. At that same distance away, you'd hear the air blast after about 3 minutes, 100 decibel intensity. Again, just to give you a point of reference here, the recent Tonga eruption, which is shown here in the image, was about 1,000 times smaller than the NADIR event would be. So again, another reference point. This was the largest sound that's been formed on Earth in the last century or so, since Krakatoa erupted. So again, just a reference point for what this is kind of outside of our historical experience for something like this to happen. Again, that same 50-kilometer distance, the earthquake would be equivalent to about a magnitude 6.5 to 7 earthquake. So that would obviously cause, depending on what was nearby, that would cause some considerable damage. Potentially also triggering underwater landslides, given its situation. And then, as shown from the numerical model, if you were looking at the water column there, we've got this enormous initial kind of peak tsunami, and then that propagates away to form this rim wave tsunami of, you know, some many hundred meters. Like at this distance of about 10 kilometers, it's still 2 kilometers high, but obviously that would collapse and propagate away with a lower wave height. But even as far away as South America, the model suggests that would be about a 5-meter tsunami. So this is a trans-ocean tsunami caused by this event. And, you know, potentially also amplified by the pressure wave, as we saw recently with the Tonga eruption, where that amplification led to a global, a small but global tsunami in that example. Another curious and interesting feature of the stratigraphy here, the target stratigraphy, is, as I mentioned already, we've got this 400-meter thick unit of black shales sitting just a little distance below the seabed. So in the case of Chicxulub, as you'll know, the emission of these sulfates and soot led to a massive scale global cooling event, catastrophic global cooling event of about 25 degrees Celsius. In the case of NADIR, we have rather the opposite. So the collision would likely liberate a large amount of methane from kind of the instantaneous conversion of those kerogens into methane. That hasn't been quantified, so we don't know what kind of effect that would have on the atmosphere. Whether it's large enough to cause a global effect is probably unlikely, but I just wanted to lay that out there. But also the potential for significant slope failure, which we can see here. If I just turn the pointer on again, we can see evidence of submarine landslides contemporaneous to that event. So the potential for significant slope failure and potential liberation of hydrates in association with that could amplify that effect. And that's something that's been proposed for the Araguña impact in Brazil. So just to kind of summarize all that in this schematic cartoon form, we have an impact at 20 kilometers per second, causes this large fireball. The shock waves propagate away from the crater and cause an earthquake. That's quickly followed by a large tsunami of hundreds of meters in the near field and something like 5 meters or so at the other side of the ocean. And that then collapses back in the water masses collapse back into the crater, bringing that sediment back into to fill the crater. So that's the model. That's what we think is potentially there. But the other, so that all deals with the consequences, the potential consequences of this size of marine impact event. But what about the relationship to Chicxulub? So we have 3 kind of working hypotheses, three and a half, if you like, working hypotheses as to what the relationship might be. We already know that there's a large impact event at that time. That's Chicxulub, obviously, at 66 million years. We also have Baltish, which formed at about 65.4 million years ago. The Nadir crater is estimated to be around 66 million years old as well, plus or minus 1 million year. But one hypothesis is that this could be just part of the background impact cratering process, right? So if it's if the impact frequency for Nadir is approximately once every 700,000 years, using this same chart, then if it's within 1 million years, we would expect to find another event sometime within 1 million years. So that is a possibility. However, that if Nadir is confirmed as an impact crater, we would then have 3 craters of 3 complex craters within 1 million years of each other, potentially, and 2 of which have a much longer recurrence interval. So Baltish is already a 3 million year recurrence interval. So there's already it's not statistically robust, but an interesting above average frequency. And bear in mind also the cratering rate, which is maybe 2% or so. So in order to kind of rule this out or to confirm this, we'd really have to find out the precise age of Nadir. A 1 million year uncertainty window is a little bit too broad. But as I alluded to there might also be the potential that this is a part of an impact cluster. So what if Chicxulub, Baltish, and Nadir are all genetically related, and that's something like what happened during the Ordovician? So perhaps there was a collision in the asteroid belt, and that led to a flux of asteroids, of smaller asteroids coming in to near Earth orbit, into the inner solar system, and those colliding with the inner planets over the course of perhaps a couple of million years. We know that's happened once already in the Ordovician. Could there be another one at the KPG boundary? So that's what we call the little cousin hypothesis, or the impact cluster hypothesis. The other possibility is that it could be part of the same event, but that the breakup occurs much closer to the Earth, so i.e. Directly because of the Earth's gravity. This is what we call the little sister hypothesis, or asteroid breakup hypothesis. So what's curious about this is that the craters are really quite far apart. The other binary impact event that I mentioned earlier. The two craters are very close together. That's what you would expect if a binary asteroid comes in to have a direct hit with Earth, right? So if the asteroids are pulled apart at the point at which, within the Roche limit, at the point at which Earth's gravity is starting to have a discernible effect on their on the attraction of the two asteroids to each other, that they're broken apart. Well, in that scenario, we would expect the craters to be rather closer together. In fact, within 100 kilometers or so of each other, or a couple of 100 kilometers. So obviously, in this case, the distance is much larger. It's about 5,000 kilometers. The Atlantic was narrower at the time, but not as close as would be required for this. So the analog we have here is the Schumacher-Levy collision with Jupiter back in 1994. And I'm not sure how many of you remember this event, but I do, which shows, I guess, my age. But in this case, the comet that eventually collided with Jupiter actually interacted with Jupiter's gravity field several years earlier. So when it came into near Jupiter orbit, the gravitational pull of Jupiter broke apart the comet, and those fragments just went round again. In another round of the solar system came back and collided with Jupiter over the course of about 9 days. So this kind of scenario where you have multiple fragments colliding over a period of days is there is a precedent for that on historic timescales. So could the same thing have happened back at the KPG boundary? Obviously, this is the thing that the media picked up on, and that's gathered the most interest about this, is the possible relationship with Chicxulub. So I did a series of interviews, as did my co-authors, around the time this was released, and we have quite a number of different articles covering this, and most of the coverage was pretty good and quite nuanced. So in this case, New Scientist, a second asteroid may have struck Earth when the dinosaurs died out. Maybe the crater may be the dinosaur killer's baby cousin from the BBC. Another asteroid struck the late dinosaur era, and so on. So all reasonably reflective of the fact that it's a possible crater and that there's an interesting temporal relationship with Chicxulub. It starts to get a bit more frayed as you get into the tabloid news. So in this one, this is one from The Sun, which is a tabloid newspaper here in the UK, who like dramatic headlines. But actually, a couple of the headlines start to get a little bit misleading. So not one, but two asteroids might have slain the dinosaurs. A second asteroid responsible for the dinosaur extinction. I mean, could that have been the case? Is it large enough to have contributed to the extinction? So what I've done here is I've just compared the statistics from NADIR and from Chicxulub together, side by side. And just to give you an idea of the difference in scale between these events. So NADIR is about 400 meters in diameter. It's about 20 times smaller than Chicxulub in diameter, many times smaller in terms of mass. The crater is a little bit under 20 times smaller. The amount of energy released is 5 orders of magnitude larger in Chicxulub. The earthquake produced is probably for Chicxulub a magnitude 11 or 12 earthquake. Again, something like 5 orders of magnitude larger, moment magnitude larger than NADIR. And then much more rock vaporized. This is probably an underestimate for NADIR. So the summary is that this was really likely to be completely dwarfed by Chicxulub if they occurred at the same time. So NADIR on its own would likely have a significant regional impact, but unlikely to be global, particularly when occurring alongside Chicxulub. Unless NADIR and Chicxulub are just two of a cluster of, I'm not talking here about a long-lived cluster, but a Schumacher-Levy type scenario where there were multiple impactors in a very short space of time. So that might be the kind of the smoking gun. Okay, I'm nearly done. Just some final thoughts on what we're going to do next. So the next steps of this are the first thing that we, in fact, I submitted this proposal before I submitted the paper, just because it's a super candidate to drill with the JOIDES resolution or through IODP. It's 300 meters below the seabed, so very accessible by ocean drilling. It can be done. This is an APL proposal, so it's kind of a bolt-on proposal to a larger proposal, which would only require about 7 days of ship time. So that's what we've proposed to do: to go and drill in, test the impact crater hypothesis, and really date the crater much more precisely. The second thing we're doing, and actually I've just received this data about 2 hours ago, is this 3D data across the crater that has been acquired by another seismic company working in the region. So I'm really excited. You know, I've got to go home to my family tonight after this, but tomorrow I'll come in and start interpreting that 3D data in earnest. I have seen the data already, and it's really fantastic. Absolutely unprecedented imaging of the structural complexity of a medium-sized impact crater. So that's all part of a NERC project that we've got running here at the moment to develop a drilling proposal in the region. And the final thing I wanted to leave you with to think about is this idea that there might have been other near KPG impacts. So we know that there was Chicxulub at 66 million years ago, Baltish at 65.35. NADIR is approximately 66 million years in age. Could there be anything else? One candidate here in Northern Europe is the Silver Pit crater, which is somewhere between 70 and 44 million years ago in the North Sea. Not a confirmed crater as yet, but quite a promising candidate. Another one that I came across recently is this one in the Tefe River impact structure in Brazil, which is published in a kind of extended abstract, really, that was published a few years ago by some people from Petrobras in Brazil. And again, here the geometry of this really looks quite promising, and this is about 15 kilometers in diameter. Its age is approximately 66 million years. There's a large unconformity between the Maastrichtian and the younger tertiary sediments, but quite an intriguing impact structure. So, you know, there's a potential. We're talking about future collaboration, maybe the potential as part of this larger quest to understand the KPG extinction event, maybe even also a future ICDP intercontinental drilling proposal in this region. So I'm going to leave you on this slide open. Happy to take any questions that anybody has. This image here is the credit is here on the right hand side, but this was a cartoon somebody published within about 4 hours of the paper going live, and I came across this on Twitter. So I'm quite impressed with the speed at which some people are doing live science journalism. In this case, I suppose this would have to be NADIR if this was dodging a bullet. But I'll leave it there. So thanks again, and please feel free to ask any questions.
Well, thanks very much. Very interesting. And we have already some questions and comments. Well, with thanks and congratulations for the finding and the study. Let me try if I can.
Yeah. I don't see the. Yeah.
Organizing them.
Yeah. Sure. Yeah.
But well, we have some questions about offshore craters. But you mentioned it that there are very few documented. Why is this? Are they not preserved, or they are more difficult to find?
If I go back here, Yeah, probably both. So obviously they should form the majority of craters. There should be about 70% of them. One issue is preservation. So you know, the oceans are being constantly recycled. The ocean in the crust has been recycled every, whatever it is, 150 million years on average. So we don't really expect to find very many old craters on oceanic crust. Nadir is not on oceanic crust; it's on a continental crust. But in fact, there aren't any confirmed craters on oceanic crust. The other marine craters are Mjolnir up in the Arctic. Chesapeake is partly marine. I mean, Chicxulub is partly marine, probably. And then one or two others that are now onshore, and actually they're exposed onshore now in Eastern Europe. But they're really very few. So part of the reason is probably crustal recycling. Part of it is preservation. So if an asteroid hits the water, the crater actually forms first in the water column, right? So it needs the asteroid needs to be large enough, maybe at least a quarter of the thickness of the water column or a fifth of the thickness, in order for the crater to form at the seabed, not just in the water column. So that's part of it as well. And the other thing is there's much more data onshore, right? The craters onshore, you can physically go, you can touch the rocks. It's okay, sometimes some of them are buried, but you can often see them at surface and explore them. So I think that those things combined.
Okay, thanks. But there are some questions related to this. Well, there are some comments on the hydrocore simulation, which they find very, very interesting. And one of the questions is about the effects of the water depth. What happens at the deeper water depths? The energy is attenuated, or what happens?
Yeah, so again, it comes back to the relationship of the size, the diameter of the asteroid to the thickness of the water mass. So I can quickly put on my, you can sort of start to see that in some of the simulations. Maybe not that clearly, but let me go back to share that screen again. If you can see here, actually it's not shared yet, there we go. You know, if you get much deeper than this, the more or less all of the crater forms in the water mass. So for this size of asteroid, if you get above about 2.5 kilometers water depth, you wouldn't see any, you know, that plastic strain would all be, it's not really correct to talk about plastic strain in that case, but the deformation would all be in the water mass. The transient crater would form in the water column, and then it would resurge and there'd be no discernible crater. You can sort of see it in that the total plastic strain is, you can see it extends right down to the base of the model in this case. And even though much less of the model is preserved here, you can see that it's getting shallower. So, you know, the orange unit here is much of very high levels of total plastic strain. Is much thicker here than it is here. So the crater size and will reduce gradually with increasing water depth, and eventually it will just disappear and there'll be no crater.
Oh, okay.
That wasn't an issue for Chicxulub, right?
No, it was well, the target was shallow.
Shallow, and the
yes.
asteroid is 13 kilometers in diameter, so it's there's nowhere on Earth that's deep enough to stop it. Yes,
yeah, and well, very well, possibly the water was vaporized. With the extreme temperatures.
Yeah.
But it's interesting to compare what happens, and it will be good to have simulations using what happens at the deep ocean floor.
Yeah. There's a good paper that discusses this by Thomas Davison et al. I think it's I can't remember the year, but he's from Imperial College, from Gareth Collins's group, and they've run simulations at all sorts of water depths for craters, asteroids of different sizes, and they model so for marine target impacts, they have a really good range of crater dimensions in that paper. I can share the link if anybody's interested.
Okay, yeah, thanks. It will be very helpful.
Yeah.
Well, we have some questions actually from the students in the Chicxulub group. Questions regarding to the structure and the possible asymmetries of the crater. The model about the seismic lines you are showing show a more or less symmetric crater.
Yeah.
But are there any asymmetries? And there are several questions related to this about if it was a vertical or an oblique impact.
Yeah.
What is your opinion?
Yeah. So you would expect again a great paper by Thomas Kenkman, I think, from a few years ago on the structural geology of impact craters. He talks about this. What kind of angle you would need, what kind of angle of incidence you'd need for to form an elongate crater or non-circular crater. It's actually surprisingly very, like, you will form a circular crater anything down to about 15 degrees. So angles shallower than 15 degrees, then you would start to form an elliptical crater. But anything shallower than that is circular. So all we can say initially is that it looks circular, and actually from the 3D seismic, it is circular. But all we can say is that somewhere between 90 and 15 degrees, which is quite a wide range. But there are subtle asymmetries. You can start to see subtly some of these here. Not so much on this line, actually, very well, but there are asymmetries in terms of the amount of the extensional faults that form on one side versus the other. It's not super clear here, but there are thrust faults. Again, these are much clearer on the 3D, and hopefully I'll be able to share that at some point soon. There are thrust faults that form over here that are not present on the other side. So they're largely extensional faulting on one side, largely compressional faulting on the other side. Tight isoclinal folding in places that's not symmetrical. So there is an asymmetry, and we don't think it wasn't purely vertical. We think it came at some angle, probably from the northeast, based on the divergence on the thrust faults and the relationship of thrust faults to the extensional faults and so on. We're hoping to be able to write that up, and now that I have the seismic in quite quickly in the next few months, and share some of those results. But yeah, there is an asymmetry, but it's only really when you can image it very well with a 3D survey that you can see it.
Okay. Well, there are actually some questions about the trajectory, if it can be defined. And you're mentioning that the trajectory is from the northeast.
Yeah, very preliminary, because I haven't actually interpreted the data. I've just seen images. I've taken some images and reconstructing based on those images. It looks like that. So I think in the case of Chicxulub, maybe it came from the northwest. Is that correct?
No, actually, the new indications is a joint study with Gareth Collins. Actually, we have all possible trajectories proposed at one time. But the last study from with Gareth Collins is a trajectory from the northeast.
Oh, okay, that's interesting. Yeah.
Yes.
Okay. Yeah.
It has been very difficult to define just using the crater asymmetries because as you mentioned, well, yeah, and it also depends on the target characteristics.
Yeah, we're very fortunate here in that the stratigraphy is very simple. All right, so it was very kind of layer cake flat-lying stratigraphy that's then deformed, and so you can there is a little bit of structural inheritance from some extensional faults that sit underneath it. You can maybe see some of them here. These are older extensional faults, so they complicate it slightly, but by and large, it's kind of like a sandbox model. So with relatively under-consolidated sediments at the time. So it's very helpful. Again, some of the papers by Thomas Kenkman and co-authors from Germany have done some great work on structural characteristics of impact middle-sized, medium-sized kind of complex impact craters like this. And the observations are very consistent with what they see, and that we think that will help us to define an orientation or trajectory orientation.
Yes, but there are some questions actually related to this image. In the case of the Chicxulub impact, there is an unconformity associated to the impact. Are there any indications of how is the stratigraphy on top of the Cretaceous?
Well, it's a very, very interesting question, and I'll show you on this line. I'm not sure how well I'll be able to address it here, but there is an unconformity at the top of the Maastrichtian, and I've been puzzling over that because I don't think Chicxulub is obviously a much larger event with a and the tsunami you're talking about, like the amount of energy associated with the tsunami and the resurge is enough to erode significantly the seabed. But Nadir is smaller, so you might expect a bit of erosion associated with the tsunami, because if you've got a 2-kilometer high tsunami wave, then it's also going to, it's going to be impinging on the seabed, and that will cause localized short-lived erosion. But it's not really like you've got significant exhumation like you do in Chicxulub. There's just the central uplift. Central uplift comes up, everything else sort of collapses in a bit in the kind of annular trough around it. And outside of there is just really outside of the crater. What could occur outside of the crater? The only thing I can really think of is the tsunami stripping away some of the surface sediment after it impacts. So yeah, I've puzzled over it a little bit, but there is an unconformity, and it extends right the way up to at least here. You can see that this reflection, for example, is cut by, although there's also a bit of convergence going on, like it's a more condensed interval here as well. So that's something that we have to kind of think through a bit more, I think. Could that just have been caused by the tsunami?
Oh, okay. Well, it's really interesting, and it's nice. You have now a 3D seismic survey.
Yeah.
That will be really interesting to look at.
Yeah. It's very exciting. It's just that it happens to cover the whole crater as well. Obviously, it wasn't acquired for that, so but it's very fortuitous. Yeah.
Yes. Let me check. There are some questions about the ejecta and the possibility of finding ejecta on land. What is your opinion if it will be possible to?
Yeah, so on land at the assuming the shoreline is somewhere not too far from where it is now. I mean, the shoreline would have stepped across the shelf and back again multiple times. So I'm not exactly sure where it was. The shelf edge at the time is very, very close actually to where it is in the present day. It is something we've thought of is to look for evidence from the cuttings from like some of these wells here that cut across that interval. I'm not aware of a KPG sequence in the near land area. I mean, the airborne ejecta, the kind of continuous ejecta blanket is only another kind of crater's diameter or two away, there is a kind of high amplitude reflection that extends right across much of the plateau of the terrace. So we think that might be partly remobilized, like ejecta plus tsunami reworked sediment. But onshore, I think what you'd expect to find is something like a dispersed tektite strewn field, something like, which we see in the case of the, I forget what it's called, Botswana or something, this crater in Cote d'Ivoire, and a couple of thousand, similar size to this, and a couple of thousand kilometers away there are tektites. But whether that's just, to find those in that layer, and then if it's KPG in age, then how do you distinguish them from Chicxulub? That's a slightly tricky one, but it's a good idea. I'd like to try and find direct evidence in some of these wells around here. The other place we thought of looking is the ODP wells over here, and they have seismic that extends across those wells as well. But in that case, there's no KPG sequence in either of those wells, unfortunately. So there's an unconformity, and the other one doesn't quite get there. So yeah, it'd be great to have some stratigraphic sequence where we want to look for evidence of this for sure.
Yes. Okay. There are some questions. If are there any indications about the type of asteroid, if it was a chondritic meteorite? And I think they were they made the question at the time you were showing the different types of asteroids, like the Bennu asteroid.
Yeah.
So they are thinking if it was a solid body or a fragmented one.
Rubble pile, or that's very hard to say. I mean, we modeled it as a chondritic asteroid. We modeled because, well, we modeled it as an asteroid rather than a comet because they're more, asteroid collisions are much more common. We modeled it as, and rather than an iron meteorite, we modeled it as a stony meteorite, just partly because of it's the most, it's kind of a base case scenario, if you like. It's the most likely scenario, but not by any means certain. I mean, you could replicate probably this crater shape with a smaller iron asteroid, for example. So the answer is really that we don't know. Our assumption is it's stony, but we don't know. I think Chicxulub is a chondritic asteroid, I believe, right? Yeah.
Yes,
carbonaceous chondrite.
It is, and actually it will be interesting to, well, if we can define which type of asteroid was because of the genetic, the possible genetic relationship.
Yeah, it would be, yeah. Well, you never know if we get lucky when we drill. I know that with the Chicxulub, not much of the asteroid is preserved in the core, right? None of it. So I think there's some tiny fragments and other inclusions in other places that and I guess also maybe the chemistry tells you as well. But
yeah, it's actually the ejecta in the distal sites.
Yeah. So actually, we had planned, when I first submitted the drilling proposal, I had planned to drill. We had two sites. One was here through the middle of the crater, and one was in the ejecta blanket over here. But because the crater's not, it's not confirmed as an impact crater, so they preferred to reduce the scope to first test the hypothesis that it's actually an impact structure, and then we can do a bigger project around it.
Oh, okay. Well, there are actually some questions about the drilling project. If you are planning to drill into the central uplift, and what the objectives will be.
Yeah, so indeed, I don't know if I've got to have all the objectives in here somewhere. No, I don't. So yeah, the plan is it's been a lot of compromise because also what it's like with IDP. There's a time is money, and you can only have so much time on the drill ship. So the compromise has been to drill through the crater floor right? Which we think this is probably all infill. Like this is probably late research deposit. This is something like swavite or impact breccia. We think is hypothesis, and then we want to drill into the black shales to test this idea that they're high in organic carbon, and maybe start to constrain models of methane emissions. But I wanted to drill right the way down through this unconformity to capture that whole sequence and to also date this unconformity. But that was pushed back, scaled back. IODP just wanted to drill to the crater floor to here. Eventually, we compromised to something off structure to about, I think, to about this depth here, where the 350-meter annotation is. So I think it's about 700 meters in total drilling depth. With about yeah.
And plan is to do continuous coring.
Yes, yeah, continuous coring from the seabed. Yeah, so the sequence in here would also give you a nice. This is Topoligocene Basoligocene. So this is all Paleogene. So this sequence is also very interesting for paleoceanographers and climatologists in terms of Paleogene hothouse conditions, and then potential recovery of life sequence maybe within the crater floor. That's one of the objectives, is to see whether, if it's the same age as Chicxulub precisely, then this will give another high resolution record of like recovery of life post KPG extinction event. Another key objective is to date the sediments, to date anything that we can find within the crater, so any impact glass or any recrystallized minerals that are within or below the crater floor. Obviously biostratigraphy and so on as well, to date that as well as possible. So there are some paleoclimate objectives as well. Those are some of the key objectives, but those are related to the shallower interval. I'm trying to think what else. Obviously to date the impact structure, to test the hypothesis that this was, what the climate implications are of an impact of this size in this kind of with these kind of high TOC shales. Yeah, so that covers most of the objectives, not quite all, but most.
Yes, well, it will be an interesting multidisciplinary project. Which is always more interesting. Well, thanks very much for the questions and the comments, and also the congratulations to Dr. Nicholson. We very much appreciate your comments as always. And thanks to the students from the different universities. It's always nice to have students following us. And also best regards from the different body from the US, Argentina, Brazil, where we have a lot of impact craters. Very different ones. And thanks to Professor Nicholson for accepting the invitation to give us this conference. And we look forward to continue and expanding the collaboration. We are planning workshops on Chicxulub, and it will be great to have Dr. Nicholson involved. So thanks very much, and we are closing the conference, so we will ask our president, Professor Meade, to close the conference. And or I don't know if do you want to say something, Uisdean?
Oh, just thank you for the invitation. I'm really interested to see where this kind of collaboration could go, and I'm very happy to discuss this with you today. And I'm very much looking forward to seeing what the future plans are on Chicxulub as well.
Oh, well, thanks. And we are extremely interested and happy collaborating with you. Y por favor, profesor Meade, si nos puede
thank you very much,
cerrar la comprensión.
Professor Nicholson. It's been a very great explanation of this very important problem. I would like to ask first to Dr. Jaime Urrutia if he would like to give us some comments, because he's an expert on Chicxulub, and there are some remarks that maybe he would like to do, bearing in mind that maybe the two are very close in time. So, Jaime, if you would like to make any comments, we would be very, very pleased.
Well, thanks very much, Dionisio. Actually, I well, became really interested when I first knew about the finding of the NADIR crater. I like the approach, and the resolution of the seismic lines is really very good. So it is an impact crater. And we are collaborating with one of the co-authors of Dr. Nicholson, with Sean Gulick, who actually gave us also a conference in this seminar series. So we talk a lot about this, and Sean is convinced that, yeah, it's a really interesting finding. And this is, well, one of the reasons why we invited Dr. Nicholson to give us a conference on his study. And we look forward to have a close collaboration. We are actually already collaborating with the Heriot-Watt University in Edinburgh. Professor Pelosi, Beatrice Pelosi from the mathematics department, she gave us a conference in the seminar series, and we look forward to increase our collaboration. And the Heriot-Watt University hosts one of the research centers, the Lyle Research Center, with the Geological Survey. And we have been working with the Geological Survey. Actually, the drilling in the case of Chicxulub, because of the shallow waters, was technically coordinated by the ECHORT and the British Geological Survey. So yeah, we are extremely interested, Dionisio, in increasing the collaboration. We will actually talk more about, we will be really interested in inviting Heriot-Watt University to join the consortium. That will be great. So overall, thanks, Uisdean. It's a real pleasure. Well,
yeah, my pleasure. Yeah, thank you. Thank you for having me.
Your conference. Muchas gracias, Dionisio.
No, hombre, al revés. Muchas gracias. Y realmente esto acredita pues, la importancia de que tengamos esta red de universidades vinculadas a través de un consorcio. La verdad es que, como lo hemos subrayado en otras presentaciones, se trata de investigaciones en curso, las que nos presentan cada martes. Y justamente el sentido también pues, es que puedan comunicarse entre los propios científicos que están haciendo la investigación. Y es bien interesante que pues, el doctor Urrutia, que es un gran experto en el caso de Chicxulub y en otras muchas cosas, pues se sume también a las investigaciones que está haciendo también el doctor Nicholson, que también es experto en este NADIR y en muchas otras cosas también, y que entre ellos pues puedan comunicarse. Y como mencionaba Jaime, pues tenemos audiencia de Brasil, de Argentina, de Estados Unidos, seguramente también en Escocia, en el Reino Unido y en otros países. Y si ustedes pueden intercambiar opiniones a través de las presentaciones que se hacen en este consorcio, pues nosotros nos sentiremos muy contentos y muy favorecidos, porque este es precisamente uno de los propósitos del consorcio. Y también lo es, y yo creo que se aprecia con esta comunicación entre científicos, que los jóvenes puedan encontrar en este espacio que ofrece la educación superior muchos nuevos espacios de conocimiento. Aquí hay temas fascinantes, los hay desde el punto de vista de cuándo se generó y cuál fue su impacto en uno y otro caso de meteoritos, pero cuál es el impacto en la Tierra, que a veces pues parece no moverse porque diario vemos las mismas montañas, pero se trata de un planeta vivo, y ese planeta vivo pues está explorando, está cambiando, y si eso pasa en el planeta, pues cuánto y más en el espacio que nos rodea, que cada vez nos ofrece más espacios de conocimiento, más espacios de investigación y más fascinación por la ciencia. De manera que pues agradecemos mucho esta presentación, agradecemos a Jaime, a Araxi, que nos hagan favor de convocar a estas mesas redondas, agradecemos al Colegio Nacional y en este caso al profesor Nicholson, que nos haya hecho favor de compartir su investigación y su conocimiento con nosotros. Muchas gracias a todos y esperamos seguir contando con ustedes. Tenemos un enorme desafío en tratar de armar un programa interesante el próximo año y seguramente seguiremos contando con el interés de la audiencia, que es lo que principalmente nos motiva a seguir adelante con este proyecto. Muchas gracias a todos de nuevo y muy buenas tardes.
Muchas gracias.